Every time you check a health portal, authorize a bank transfer, or send a secure message, you are relying on an invisible shield. Our entire global infrastructure rests on hidden layers of cryptography, quietly keeping out intruders. Encryption works by applying a one-way mathematical function to your data. This process scrambles your private information into a randomized string of characters that can only be unscrambled by someone holding the corresponding mathematical value. Currently, we trust these systems because of the time required to solve them. For a classical computer to guess a modern 128-bit sequence through brute force, it would need to run calculations for millions of years. But the hardware landscape is shifting. Today, laboratories around the world are engineering a new class of machines designed to bypass the computational limits of classical silicon processors. By trusting our most permanent, long-term secrets to mathematical barriers that have a clear expiration date, we have set a quiet timer on global security. These machines are quantum computers. Instead of processing information in simple binary lines of ones and zeros, they use qubits. Qubits operate on the principles of quantum mechanics, existing in multiple overlapping probabilistic states at the same time. A classical computer approaches a puzzle linearly, testing one candidate at a time, a process that makes finding the correct value impossible within a human lifetime. But when a quantum system applies Shor's algorithm, the computer identifies factors simultaneously, resolving the puzzle in moments. This approach exploits quantum interference to isolate the correct solution. It effectively ignores the difficulty of the mathematical problem, rendering the original defense irrelevant. To understand our vulnerability, we must examine the two distinct encryption types keeping networks secure: symmetric encryption for hiding bulk data, and asymmetric encryption for verifying identities and distributing keys. Symmetric encryption is resilient. By doubling the bit length from 128 to 256, we increase the number of possibilities to a level that remains difficult for even a quantum machine to resolve. This diagram illustrates the divergence. While the symmetric stream survives by increasing its complexity, the math behind asymmetric encryption collapses. Larger keys do not help here. The prime factoring logic that protects our digital certificates becomes transparent to a quantum computer. This threshold is known as Q-day. It is the calendar date a quantum system reaches the sustained power necessary to execute this specific break against the world's asymmetric infrastructure. A failure of digital authentication means a total loss of verification. We lose the ability to prove software updates are safe, confirm digital contracts remain unaltered, or maintain trust in global banking. Experts estimate Q-day will arrive between 2030 and 2035. However, because this is a matter of national security, a state-sponsored actor could reach this capability in secret long before any public announcement. The threat isn't waiting for the hardware to arrive. Through a strategy called Harvest Now, Decrypt Later, adversaries are engaged in the active collection of encrypted data from secure servers right now. They are essentially stockpiling encrypted files today, betting that the data will still be valuable years from now when they have the hardware to read it. If a medical record or a corporate trade secret was copied last year, its eventual exposure is already determined. The compromise happened in the past. The world is simply waiting for the technology to catch up to the theft. Modernizing our defenses is a massive inventory task. A typical organization relies on thousands of unique cryptographic instances, many of them hard-coded into legacy software or hidden in third-party tools. As this map shows, the conversion process is slow. If an IT department updates one instance per day, the total migration can take over a decade. The conversion rate falls behind the advancing quantum timeline, leaving significant portions of the network exposed. Delaying this migration carries an increasing cost. As the 2030 window approaches, the scarcity of specialized consultants will drive service prices higher, forcing organizations to choose between extreme expense or leaving their data vulnerable. Protecting today's data requires an immediate transition to post-quantum cryptography. We must implement these new algorithms now to ensure that any data harvested today remains unreadable in the future. Q-day is a physical certainty. The race isn't about stopping the technology, but finishing our defensive migration before the first capable machine is switched on.